To create this video, I partnered with DesignCon. Many people ask me like, I have differential pairs, why I would need ground? Or do I really need ground? And what do you think, Eric?
I get exactly the same question. And when I talk to engineers that are just learning about differential pairs, they always tell me, wait, I hear all the time that the one line in a differential pair carries the return current of the other line. Why do I need a ground plane if I've got a differential pair? Because doesn't the other line carry the return current? There's not supposed to be any current in the plane, so why do I need a plane in there? And uh, and the most common answer to all signal integrity questions is it depends, but the next sentence has to be, and it depends on, and that's what we want to talk about today is what does it what does it depend on? In what case is the other line and the second line in a differential pair? In what case is that line carrying the return current of the first line? And in what case is there return current in the plane down below? And that's the question that we're going to address.
So when we say
And
second line, it
yeah,
means when we are talking about positive, when one is positive, then second line will be negative, correct?
right. And so when we talk about a differential pair, I always refer to it, it's one differential pair, but it's composed of two transmission lines. And we describe the two transmission lines in the one differential pair as the P line and the N line, or the plus line and the minus line, or P and N is plus positive and negative lines, but it's still the sometimes like in a schematic like USB, you label it as a D plus and D minus as the two lines that make up a differential pair. But it's one differential pair.
Okay, now I have, before we go to these slides and
Yeah.
deeper, I have two questions. So first one is I heard there is like a real differential pair and there is like kind of not real differential pair. Something like when differential pair is built from two single-ended signals, is it still like differential pairs? And is there difference between having like real differential pairs, which are just plus and minus signal and no ground is needed, or how to explain this?
Right. So, I'll tell you, the problem with these questions that you ask is sometimes it takes us off on a tangent, and we just spend time on the title slide and we talk about the answers to the questions because they're all really important questions that I encounter engineers all the time that ask that kind of question. Here's the answer. So you're asking the question, are there different kinds of differential pairs? Is there a differential pair that is two single-ended lines or a differential pair that's a real differential pair? The answer is all differential pairs, with no exception, are always two single-ended transmission lines, period. It's just about how we design those two single-ended transmission lines that give us different properties of differential pairs. But the behavior of a differential pair is fundamentally about the behavior of two single-ended transmission lines. And we need to identify when we have two single-ended transmission lines, where are the return currents for each single-ended transmission line, and how much coupling do we have between the two lines? And when we have a single differential pair that's composed of two single-ended transmission lines, when we have one differential pair, we can talk about on that one differential pair two different kinds of signals, a differential signal and a common signal. And so we have to be very careful. Usually when I talk about differential pairs, I always introduce the idea that, in fact, you know what? Let me grab that slide. I think I have it here, and that will describe exactly this question. Here it is. Okay, so this is the answer to your question you asked of, are there different differential pairs? And the answer is, there is one differential pair. It is either, here's an example of, unfortunately, this is a microstrip line. A differential pair is a multi-layer board. We're seeing the traces written in silk screen just to make it easier to see. But it's a differential pair. It is also two single-ended transmission lines with some crosstalk or coupling between them. And so we have to be careful when we describe a differential pair, we have to be a little schizophrenic, but keep our two minds very separate. It is either two single-ended transmission lines with crosstalk, or it is one differential pair. We can't use both terms in the same sentence at the same time. It's one or the other. And when we talk about two single-ended transmission lines, then the signals on the two lines are single-ended signals. There's a single-ended signal on line 1, a single-ended signal on line 2. They can be arbitrary, absolutely anything we want them to be. If we describe those same two single-ended transmission lines as one differential pair, then we can only describe the two kinds of signals, a differential signal or a common signal. That's it. And so we have to be really careful keeping, that's why I say, oftentimes, I teach a circuits class for sophomores and freshmen at CU, and we just talked about time domain and frequency domain. And I told them, you have to learn as an engineer to be schizophrenic. You have to keep two equivalent concepts in your head at the same time that are completely different. Time domain, completely different from frequency domain. They're equivalent, don't mix them. Same thing with differential pairs. You have two completely separate concepts that are equally valid ways of looking at things. Don't mix them. There is either two single-ended transmission lines that have crosstalk, and you have single-ended signals, or it is one differential pair, and you have differential and common signals on it. And so you just have to be careful not mixing the two concepts.
So if I understand right, basically it is same situation, but you can have two different looks at this situation.
Yep.
Okay.
Exactly the same transmission lines. I mean, these are literally the same lines. We are looking at them, thinking about them, analyzing them as either two single-ended transmission lines with crosstalk or one differential pair.
Okay, then I have another question.
Yeah.
So
okay.
What if this differential pair goes through a transformer? So transformer output from the transformer would be just plus minus. There is no ground or anything else. So is it different from?
Well, so you might think that, but there is, what is the Monty Python line
There is always
about?
ground. Eh?
Yeah, there's always ground, right? And that's where we have to be thinking about. Remember, I said when you have a differential pair, there are two kinds of signals. There's the differential signal, there's the common signal. And they can and any arbitrary signal that we put on the differential pair, we can describe as combinations of those two and only those two. And the common signal will and the differential signal as well. There will always be a return path somewhere in the system. You may not like it, you may not know where it is, but absolutely guaranteed those signals are going to find it. And if you don't engineer it, you're probably not going to like what they find. And that is the most common source of EMI problems, of crosstalk problems, of discontinuity problems, is the poor engineered return paths for those differential pairs.
Does it mean that, for example, in this board differential pair routing and this transformer differential pairs, there is a different kind of influence of these two different situations? Like, for example, in transformer situation, we may consider this as a differential pair more, or effects from differential pair will be bigger than from two single-ended transmission lines, or no?
Well, unfortunately, that's another one of those it depends kinds of answers that, you use transformers for, a lot of different things, but when it comes to signal path, it's typically two kinds of things. One is as a balun, and a balun is a component that will convert a single-ended signal, a single-ended signal into a differential signal. That's or vice versa. So that's one application. The other application is isolation. Actually, three applications, I guess. Isolation of the signal, and the third is filtering. And if you have a like Ethernet, for example, is multiple differential signals coming off, and I'm going to show an example in a minute here of Ethernet cable, twisted pair cable, and And there, in order to, the number one most common source of failing, root causes of failing an FCC EMI certification test is common currents on external cables. And if you use a unshielded twisted pair for Ethernet, and I'm going to show you an example here in a minute, use unshielded twisted pair for Ethernet. If you drive it with a pure differential signal, there is no common signal. You don't fail EMI rated emissions. But if you have any common signal on that external unshielded twisted pair, 99% of the time, that's the source of failures for FCC.
Come
And
on,
it only
go ahead.
it only takes about 3 microamps of common current to fail an FCC Class B test, similar to CISPR test.
I think we
Is
should, yeah,
tiny amount of common current.
we should clarify what common means, because it means that there is some kind of DC voltage or something like this. Can we say like?
So I wouldn't say DC, but here's what common means. And so I don't have a slide to show what they are, but we can talk about it. But I do want to emphasize how important the words are that we use to describe those signals. And it's important in influencing how we think about things. And so that's why I'm very careful to use that term differential signal and common signal. Don't use that term, which I hear over and over again in the industry, differential mode signals and common mode signals. I mean, EMI guys have used this historically, and I'm never going to change them. But I think it's really important, if you're a signal integrity engineer, get in the habit of thinking differential signal and common signal, because it forces you to think about the signals, not the interconnects. So you asked, what's a common signal? The differential signal, if I have these two transmission lines, line 1 and 2, single-ended transmission lines, I have a single-ended signal on line 1, single-ended signal on line 2 with respect to reference ground somewhere, my circuit ground somewhere. And so I have we call it line 1 or the P line and the N line, the differential component. So now we have as the single-ended view, we have a voltage line 1 and line 2, that single-ended view. When I translate that to my differential view, I have a differential signal component, which is literally the difference between them. And I have a common signal component, which is literally the average. That's what we mean by the common signal is the average. And I can literally take any combination of two single-ended signals and just literally calculate at any instant in time what the differential component is and the common component. And so the common component could be modulating just as fast as the differential component. It just means common just means the average.
Mm-hmm.
If my two differential signals are a 0 to 1 and a 1 to 0, those are the two signals, then I have a differential component. A lot of people think, oh, that's a differential signal. They're doing like this, but they're going from 0 to 1 and 1 to 0. There's an average value, and that average value happens to be constant. But if there's a little time delay between when this one switches and when this one switches, now there's an average value that also switches.
And that's the
And so
problem.
that's the problem, right? It's that common signal component that gets on the differential pair, and it's only in that. It's not that I wrote an article for, I think it was EDN a couple years back, that I said common signals are given a bad rap. That common signals, yes, are the major source of rate emissions problems in FCC tests, but that's only if they get on external cables. Common signals on circuit boards, like this example, this picture here, if I have a common signal component on the circuit board, it's not going to radiate. It doesn't cause an EMI problem. It's only if this gets onto unshielded twisted pair
Because it
or
has to
on
find the ground.
because it's going to be an antenna, it's a wire sticking off,
Yeah.
and the return will be somewhere on the floor
Yeah.
or by radiated emissions, basically.
Yeah.
And so it's only in certain special cases are common currents bad for EMI. Otherwise, we have common currents all the time on circuit boards, and they cause no real problems.
Okay, so let's
So
go at the
yeah,
beginning of our slides because we only have half an hour.
yeah.
So let's have
Okay.
a look.
So we're going to talk about the special case of, hey, what about when a differential pair doesn't have a return plane? So where's the return path for it? And so we're going to look at three cases really briefly. I've got a traditional microstrip here that is, two signal lines with a nice plane underneath it. And so they're two single and transmission lines, beautiful, wonderful, great. And we're also going to look at them as a differential pair. And I've got another case where exactly those same two lines, but I removed the return plane underneath. And so this is the circuit board that is backlit. And so you can see that the dark area here means, oh, there's a solid plane underneath. Here, there's no solid plane. I've cut it out. And so it's a light region underneath. There's no plane. And so where's the return current for the differential pair, or the return path for the differential pair? And then the third case we're going to look at is, here's that unshielded twisted pair case. I literally took Ethernet cable I had lying around. There are 4 twisted pair in it. And I pulled out a couple of pairs, and we're going to connect them in different ways. So we're going to connect the 2 lines that make up the differential pair for one of them as signal and return. We're going to take the 2, and we're going to have the 2 signals isolated with the return paths here, and then the 2 isolated with the return paths, and we're going to measure from the TDR. So we're going to look at some measurements on this. And so here they are isolated, and we're going to compare how we think about them. Where is the return path for these 2, for this one differential pair? And we're going to look at that. Okay, so those are 3 examples. So we'll look at it really briefly. And to think about this case, the first case with a nice plane, that's just to get us calibrated. So, we're going to look at these situations, and, we were talking about earlier, I tell my students, hey, before you do a measurement or you do a simulation, think about what you expect to see. Exercises your intuition. And so we're going to look at this case first, where signal is going to come down here. Where's his return current going to be? Well, obviously it's in the plane underneath. And we can analyze, where is the current distribution in that plane? And here is what it looks like. So this is a actual simulation in ANSYS's a 2D extractor, where we can simulate the current distribution. I blew it up to make it easier to see. Here's a signal line, here's the return plane, and it's kind of roughly 50 ohms. And I don't remember, I think this was 100 megahertz is the frequency, and the color is where the return current is. The blue means no return current, the red means a lot of return current. And you can see in the signal, okay, it's spreading out, skinned up effect. But look in the return path, the return current is not way out here, it's underneath. And I don't know if I talked to you about it, or I've given a couple of webinars recently about return current distributions. And at frequencies in the audio range, in 10 kilohertz and below, that return current spreads out. It really is all the way around. But at frequencies above about 100 kilohertz, so above the audio range, that return current is well localized under the signal line, providing it's roughly a 50 ohm line. If I take this structure and I pull that return path farther away, so this is the aspect ratio for roughly 50 ohms. If I pull that return path farther away, what do you think? Here's the pop quiz for you. What's going to happen to the characteristic impedance of this transmission line?
I see.
If I pull that return path farther away? Well, that's the current, but what happens to the characteristic impedance?
When you pull it away, it goes higher, no?
Yep, it goes up, right? So if I pull it away and I have a higher characteristic impedance, the return current is going to spread out. And if you think about it in terms of aspect ratio, that aspect ratio, because here is a rough approximation for what that current distribution is in the bottom plane. Here is that value of D. This is how far away I look, and H is the dielectric thickness. And if this is constant, in other words, if the aspect ratio, if I look at a certain distance and it's a certain dielectric thickness, if that aspect ratio is constant, I'm going to have about the same relative current distribution. And so if you think about, here's that signal line, here's the return plane. If you think about that aspect ratio being constant, as I pull the signal plane, the return plane farther away, the current's going to spread out and
Mm-hmm.
it's going to be scaling with
Mm-hmm.
that aspect ratio. And so I pull it farther away, the return current spreads out as well. And that is the most important principle to think about when you think about the return current distribution. And here's an analytical calculation of that. Here's what that current distribution looks like under the signal line when it's in close proximity. The return current is localized underneath the signal line. And here in green is when I pull the plane farther away, and here's what that current distribution does. It still scales, so most of the return current is roughly in that, as I make the H farther away, the return current distribution spreads out as well. And that means that as long as I have a single-ended line, its return current is going to spread. Of course, its impedance is going to increase. And as a single-ended line, we got to worry about that. But the return current distribution is going to spread out as a single-ended line.
Mm-hmm.
Now, let's look at that analysis with a differential pair. And so here is again, these are simulations with ANSYS's SI2D. And these are the cross. So here's my differential pair, and here's the return plane, and I'm plotting the current distribution now as with direction. The color is direction. So the red means it's going into the board, and the blue means it's coming out. So it's signal return, and here I'm sending a differential signal in, and so here the blue is coming out and going in. Okay, so when the signals are in close proximity to the return plane. So this is roughly a 50 ohm line, or a single-ended 50 ohms. Roughly the differential impedance is roughly 100 ohms. When it's in an aspect ratio, when it's roughly 50 ohms, the current goes in, it comes out the return plane, and you can see the return current spreads out. Now, it also spreads out on this side, but the return current from this line is coming out. I'm sorry, it's coming out here. It's going in here. The return current here is coming out in the bottom in red, but it's going in blue over here. Where they overlap, they cancel out. But it's only in this small region over here where they overlap. Most of the return current is separate and succinct, and it's just the return current in the plane. And so this plane is really important in influencing the differential impedance. I need that plane in proximity to give me the differential impedance I'm shooting for, because I need the return currents in proximity to the signal lines. Yes?
So I would like to point out that even we are talking about differential pairs, there are still currents flowing in the ground plane below these differential pairs.
Right.
It's not like currents are flowing only in the differential pair tracks.
Right. And it has to do with the proximity of the return plane. When the return plane is close, that is roughly single-ended 50 ohms, roughly, then the return currents, I've drawn these, so these two lines are tightly coupled. The space in between them is equal to the line width. So this is kind of an extreme case. It's tightly coupled lines. In this extreme case, when they're tightly coupled and they're 100 ohm differential impedance, there's about 90% of this guy's return current is in the plane, and 90% of this guy's return current is in the plane. Only about 10% of it overlaps and cancels out. And it's absolutely true that where the return currents overlap, they cancel out, and we don't have any return current there. But it's only 10% of the return current cancels out. And that means that, this guy's carrying about 10% of his return current and vice versa.
So I have another question before we move to the other pictures. You already mentioned when they're tightly coupled. So what does it mean?
Oh, what does it mean? They're close together. That's all.
You can have 100 ohm impedance even when tracks are far away. You can have 100 ohm impedance even when they are closer. So what is the difference? Is the effect going to be bigger between them when they are closer, or these are the tightly coupled, these are the loose coupled, I think, correct? Right,
you're absolutely right. You can engineer the same impedance line, whether they're close together or far apart, by adjusting the relative line widths. I have a student group that I'm teaching a a signal integrity projects class this semester, and about measurements. And I had a student team build a couple of transmission lines where they're far apart and uncoupled, and then brought together really close. I mean, really close together. So the coupling between them is really, really, really high, and they had to reduce the line width by a factor of 10 in order to keep the differential impedance constant. So they went from far apart, really wide, to really, really, really close together and really, really narrow. Um, Design it for 100 ohms. Darned if they didn't get a pretty good match to 100 ohms. So whether they're really far apart and uncoupled or really close together, and you optimize that line width for the coupling, you'll get the same 100 ohm impedance. The differential signal will never know the difference. And so,
Which one is better?
right. So you ask the question, okay, if I can get the same differential impedance, what's better, tightly coupled or loosely coupled? Because it is not about achieving a target differential impedance. And so there are second order questions or second order features that influence tightly coupled or loosely coupled. For example, routing density is number one. If I'm really pressed for routing density, I want my lines as close together as I can in order to route everything there. So if I care about routing density, then tightly coupled is what I want to do. Second factor is, well, what's the downside of using really tightly coupled? Well, the downside is I'm using a narrower line. And so I want to make sure that my fab vendor can fabricate that line width suitably, with the right tolerance and without costing extra and all that. So make sure it's manufacturable. And the second consequence of a narrow line, what do you think is different about a 100 ohm differential pair with a wide line uncoupled or narrow line and tightly coupled? What's another factor that's different about the two lines, do you think?
The size
What's
of the fields between them? I don't know.
Yeah, yes, but that as long as you keep things, far enough away, there's no effective coupling crosstalk to the differential pair. The when you go from a wide line to a narrow line, what's one of the other properties of that line that's affected by the width of the line? Can you think of any other properties?
Mm,
So
no.
it's resistance of the
Oh,
line.
resistance. Yeah, yeah.
The wide is low resistance, the
Mm-hmm.
narrow is a little higher
Oh,
resistance.
so
And
this way you can control the single-ended impedance of the individual track.
Well, yeah, but I'm talking about the DC resistance, the
Mm-hmm.
actual conductor resistance, because that plays a role with conductor loss. And
Mm-hmm.
if I care about interconnect density, then tightly coupled is better. If I care about loss and in all of its forms, then I want to balance. I want to not use the tightest coupling because that means the narrowest line, and that means higher resistive loss. And if I use uncoupled, as I move them farther, I'll use a wider line. And at some point, that means a little less loss. And so if I live for loss, maybe loosely coupled is a better
Mm-hmm.
trade-off of interconnect density and loss. It turns out that crosstalk, I hear a lot of folks saying, well, I want to use tightly coupled differential pairs so that I don't have a lot of crosstalk or I reduce crosstalk in this differential pair from another differential pair. Totally wrong. And all of these topics are important topics when it comes to designing differential pairs. And you don't want to take my word for anything. You want to do your own analysis. And that's where understanding the fields, that's where using a field solver comes in to put in the numbers to do the calculations for us.
Okay, let's move here. We still have
Okay,
like 10 minutes.
10 minutes. Well, it's all important questions. And so here we make a transition. Here in this example, what I'm showing is how as we pull that return plane farther away, I'm increasing that aspect ratio, and I'm looking at the return current distribution of this single-ended line in the return plane and this single-ended line in the return plane. And as I pull that plane farther away, yep, the aspect ratio
Mm-hmm.
stays the same, but the return current spreads out. And look, in this case here, the return currents of each of these two lines have spread out so much, they overlap. And where they overlap, they cancel out.
Mm-hmm.
But I have to get, relatively far away
Mm-hmm.
for those return currents to spread out. So I have two regions. I have this region where the return plane is in proximity and the return currents are clear and succinct. The crosstalk is about, how far away the aggressor is from these two. There's not much crosstalk on, if I have my aggressor over here, there's crosstalk on this guy, not much on this guy because he's, relatively far away. And the plane is really influencing the crosstalk field lines between them. The return current's clear and succinct between these guys. Got to worry about the return plane. This is the normal way of routing differential pairs on a board. But if I can pull that return plane farther and farther away, far enough so the return currents are actually overlapping, then, oh my gosh, look, there's no return currents in that plane. They overlap. I can take that plane and I can throw it away and it won't have any influence. And as I've pulled that plane away, I've increased the single-ended impedance and increased the differential impedance of that pair. This is the environment where we have traces on circuit boards. This is the environment where we have unshielded twisted pair. They're still differential pairs. They're still two single-ended transmission lines with crosstalk. It's just two different behaviors, two different regimes because of that distance to the return current and how far away they are. And they behave crosstalk-wise now in this environment, then yeah, tightly coupled will decrease the crosstalk dramatically from an aggressor over here. If I have the return, if I have uncoupled or if I have loosely coupled versus tightly coupled for these guys, and I have an aggressor over here, yeah, the crosstalk will be influenced quite a bit by whether they're coupled or not, but that is not the environment that I have in a circuit board. So two different regimes based on where the return current is. And now, well, in this case, it is absolutely correct that the return current of this line is carried by this line. As single-ended, the return current of this single-ended signal line is carried by this single-ended signal line. And as a differential pair, all the field lines are contained in close proximity to these guys. There's no influence by the presence of a plane anywhere nearby. And the differential signal is all self-contained. What about the common signal? What if I have the same voltage on these guys? The common current is not going to, it's going to overlap, but they're going to be common. They're just going to add, and the common impedance is going to be really high. So the return current for the common signal is going to be in the plane underneath. And so this is where we have to be very careful of differential signal, common signal, and the behavior of where that return plane is compared to the space in between the two signal lines. And so as a rough rule of thumb, which is, pretty good rule of thumb, how far do you have to move that return plane so that return currents cancel out? And the answer is about a distance corresponding to the span of the two differential pair, or the two lines in the differential pair. So if I take this line width plus space plus line width, that's 3 line widths, I need to pull that return plane a line width, a space, and a line width away in order for the return currents to cancel out.
That's not really
And if
much.
that spacing, huh?
That's not much.
It's not. You're absolutely right, but it is still very thick compared to what we usually use on circuit boards. And so in the circuit boards, we have this geometry in ribbon cables, in unshielded twisted pair, in flex. We typically have this geometry. And so it depends on which geometry we're using and how we engineer the space in the return plane, whether we have this environment with this set of guidelines or this environment with a different set of guidelines. Well, that's just setting the stage. That's how we think about it. Let me show you one example because we only have time for one example here. Let me go to my unshielded twisted pair example. So because this is the extreme case. This is, I have one twisted pair here that I've connected with as a single-ended signal in the return. And I'm going to look at the TDR response. I'm going to send a signal in, look at the impedance profile. What do you think we're going to see if we look at this? It's just one signal line. Here's the return. They're tightly coupled. We're going to send a signal in. Do you think this is going to be a good or a bad transmission line? Uniform transmission line or all over the place?
Good.
I think it's going to be good too because yeah, it's not, signal over plane, but it's very controlled geometry. And I keep the same space between the signal and the return. And it's just twisted wire, that's all. So I should see a really nice uniform transmission line when I look at this length of cable. In this case, so I have two single-ended transmission lines that I'm going to drive with a differential signal. When I drive this line as a single-ended transmission line, and this signal line is going to be above literally the floor or the table that I'm putting this on, and there's going to be some coupling to the table, and the table is going to couple back through the shield here, but it's
Oh,
going to be this very uncontrolled way, and it's going to be all over the place. The single-ended impedance of this line, and likewise the single-ended impedance of this line will be all over the place. But now, when I drive a a signal on this pair, this signal goes down, the return is somewhere in the floor, it spreads out some convoluted place. I send a single and a signal down this line, opposite. One goes 0 to 1, one goes 0 to -1, so it's opposite. The return current for this guy's single-ended signal is going to be all over the place as well, but all over the place in exactly the same way this one is. So they're going to overlap, and if they overlap, what are they going to do? They're going to cancel out. And it is true that the return current for this single-ended line will be carried by this one when I drive them with a differential signal. And the differential impedance should be pretty well controlled. And so let's take a look at that. So here is those two cases. So here's A, and I'm literally measuring, this is a TDR response, literally measuring the TDR response of the impedance profile of this twisted pair. And darned if it isn't beautiful looking uniform transmission line. Because of the geometry, the space between the lines, their diameter, and the material around there, the equivalent single-ended impedance is about 100 ohms. It's a little hard to see on the scale. Here's 0, here's 200 ohms, and it's about 100 ohms as the single-ended impedance. Beautiful, wonderful transmission line. So a twisted pair makes a beautiful, wonderful single-ended transmission line if I drive a signal down one line and I drive the other line as the return. Okay? Now, let's take these two, but I'm going to take this one here, and I'm going to drive this with a single-ended signal as well. But his return is connected to the shield of this coax cable, and what's going to happen, the signal is going to go down here, the return is going to couple this, but that's just going into the end here. There's a little bit of coupling back here, but most of this line and the two of these, they're going to couple, I don't know, to the floor. They're going to couple to any metal nearby. They're going to go all over the place. And sure enough, look what happens to the singlet-ended impedance of this line. It encounters this convoluted return path all over the place, really far away. And look how high the single-ended impedance of this line is. 400 ohms, 1,000 ohms. It's all over the place. And then the open at the far end. It's an uncontrolled impedance. It's a wire sitting in space
and then
with some
C
kind of
is
coupling coming
basically
back.
similar.
Pardon?
C will be very similar.
Yes, right. Or looking at this one as a single-ended impedance of this, it'll be identical. Because his return is going to be they're close together. His return is going to be exactly the same as his return. So this line, a single-ended, this line, a single-ended, they'll be identical. And now when I apply a differential signal between them, so this is the 0 to 1 and this is 0 to -1, the return currents will overlap. One current will be going one way, the other current is going to be the opposite. They'll overlap and cancel out. It won't matter that there's no return plane nearby. The differential impedance ought to be a nice value. And sure enough, here it is. So here is, in green is the same thing I showed before, the single-ended impedance of this pair. And in blue is the differential impedance between these two. Darned if they aren't exactly the same. And so whether I have a single-ended signal with signal and return, or a differential signal with the P current going in and the N current coming out, with the return currents disappearing, the current distribution is identical between the two, the the differential impedance between these is the same as the singlet impedance between them. And there it is.
Okay. So we don't have time for anything else, but this is still useful. I hope everyone understands what we meant.
I mean, we're scratching the surface here. There's
Okay.
still a lot more to talk about.
One more thing. How does it look when you remove the ground from the PCB under the differential pairs? Can we see this?
Sure. So I'll do the same thing with this example. This is, I took the plane away. So here is the singlet and impedance. And so I send a signal down one of these lines, and its return is in here, and it goes all over the place, convoluted, really high impedance, goes everywhere. And now I drive it with a differential pair or differential signal, and the returns are going to go all over the place, but they're going to overlap and cancel out. Beautiful looking differential impedance. It's kind of high, 150 ohms, because I don't have them close enough together to give me a lower differential impedance, but given that spacing they're line width and the return being infinitely far away, it's pretty darn nice looking uniform differential impedance, isn't it?
Even okay, I understand. Thank you so much, Eric.
Okay, and I hope to see you at DesignCon. And I know you'll be at your booth and you'll be walking around. I've got a bunch of events there as well. I hope folks will come see us and come to all the events that we've got going. It's a very full program at DesignCon this coming up.
Yeah. Okay. Yeah. I look forward to seeing you there in person again. And thank you so much for explaining all this.
Okay. Hey, we'll talk some more another time. See you at DesignCon. See all of your viewers at DesignCon as well. And if any of your viewers do show up there, please stop by and say hello.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our Fedevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.